We increasingly trust AI to help us make decisions about our health, our finances, and our future. As that trust grows, it becomes more important than ever to understand how these systems behave and where they can fail. Today, the most powerful AI models are developed by private companies, and their pre-training pipelines are complex and largely opaque to outside researchers. That makes it hard for the wider community to independently assess what risks might be present. I'm Alex Sully from the UK AI Security Institute, the first state-backed organization in the world dedicated to advanced AI safety. Our mission, as part of the UK government, is to build the scientific evidence base that governments, developers, and the public need to navigate rapid advances in AI. One area we look at is data poisoning, attacks where malicious data is hidden within the trillions of words and numbers used to train AI. Because modern models learn from huge amounts of scraped web data, in principle, anyone who can put text online can contribute to a training set. That makes it worth studying how vulnerable this pipeline really is. In this project, we look specifically at backdoor attacks. This is a type of poisoning where an attacker creates a hidden vulnerability. The AI acts normally until it sees a very specific signal that triggers a particular behavior. These triggers are the keys to the backdoor. They could be a code word, a specific date, or even a unique phrase buried in a prompt. Once triggered, the AI might leak your private data, bypass safety filters, or produce outputs the attacker has chosen. Our study, a collaboration between AC Red Team, Anthropic, and the Alan Turing Institute, used Isambard-AI to investigate exactly how much bad data is needed to poison an LLM during its pre-training phase, and how that requirement changes as the models scale up in size. Accessing the Bristol-based supercomputer from London, we trained models with various different amounts of poisoned data and recorded what happened. Isambard-AI was central to the exploratory part of this work into data poisoning. Pre-training language models is computationally demanding, and Isambard let us iterate quickly and run the range of experiments the study needed. A project like this would have been very difficult to carry out without it. The results of our project took us by surprise. It was previously assumed that to poison a model, you would need to reach a certain percentage of the data trained on. So the bigger the LLM, the more effort attackers would need to put in a backdoor. In fact, we discovered the size of the model barely mattered. A tiny amount, around 250 malicious documents, was enough to install a backdoor across a wide range of model sizes we tested. What this tells us is that LLMs are easier to poison than we assumed. We're hoping these findings draw more attention to the risks of data poisoning, and that we have inspired further research into this important topic.